Hello, I'm Claire Reimers, President-elect of the Ocean Sciences section of AGU. This year's Harold Sverdrup Lecture will be given by Dr. Arnold L. Gordon in recognition of his highly influential work on global ocean circulation. Dr. Gordon is a professor at Columbia University's Lamont Doherty Earth Observatory, where he also served as the director of an observatory technical and innovation center from 2005 to 2011. His research focuses on the ocean's stratification, circulation, and mixing, and the ocean's role in Earth's climate system. He studies the transfer of heat and fresh water within the ocean and between the ocean, cryosphere, and atmosphere, with specific attention to interocean exchange and to ventilation of the deep ocean interior. Over a distinguished 55-year career, his pioneering work on global ocean circulation has been honored many times. For example, Dr. Gordon received the Prince Albert Medal given by the International Association of the Physical Sciences of the Ocean in 2013, AGU's Morris Ewing Medal in 1999, and Woods Hole's Henry Brant Bigelow Medal in 1984. He was selected as an AGU Fellow in 1989, a AAAS Fellow in 2013, and an Oceanography Fellow in 2015, amongst other honors. Dr. Gordon is also a past president of AGU's Ocean Sciences section, which is meaningful to me as it means I am following in his footsteps. His lecture today is titled Tropical Ocean to Southern Ocean Coupling, Indonesian Throughflow, and Weddell Sea Bottom Water. There will be a question and answer session immediately following the lecture. Thank you.
All right. So it's a great honor to give the Harold Sverdrup lecture here at AGU remotely. And Sverdrup was certainly one of my heroes. And I'm always amazed of how people who studied the ocean decades ago were able to learn so much about the ocean from so few data points. And I always wondered, well, every data point counted and they looked at them all. And maybe today we're flooded with so much data that something strange or some discovery might actually be lost. I bought The Oceans by Sverdrup, Johnson, and Fleming. Was the first book I bought. I started working as a graduate student at Columbia University in the summer of 1961, and the book, The Oceans, I purchased that summer. The first publication was in 1942, but there were various editions, I think up to 1955. And this Sverdrup, Johnson, Fleming provided just a fantastic global view of the spatial patterns of the world ocean. There was an implicit assumption of steady state. I couldn't do much else with so few data points. That book and Albert Defont's book on physical oceanography sort of shaped my view of the ocean. Now, my trajectory, first, the unofficial abstract I have in the upper right there, the trajectory of my career from Brooklyn to what I call upstate New York, which Palisades, New York, where the Lamont Geologic Survey, Lamont Geologic Observatory is, and it changed its name many times. It's now the Lamont Doherty Earth Observatory. And from there to the world ocean. I made observations from ships at sea, many places of the world ocean, and discovered a lot of unexpected features. I'll discuss that trajectory, and then I'll discuss some recent changes I've noticed in the Indonesian Throughflow and in the Weddell Sea Bottom Water. And my warning is I'm going to be all over the map. going to cover a lot. But first, the map of Brooklyn, 2 Palisades, that short little arrow in the left side there. Oops, so my. To me, Palisades, though it was only about 30 miles away from where I lived in Brooklyn, was upstate New York. And that, of course, led to all sorts of jokes about this. And for somebody living in New York City, it was quite common to think of New York as the center and move a little bit north of it and you're upstate. But of course, it's downstate. But however, from Palisades, from Lamont, I then traveled the world ocean. Now, I started my graduate work, as I said, in the summer of 1961. And my advisor was Georg Wüst. He was a visiting professor at Columbia from 1961 to 1963. The Ford Foundation grant supported his visit and supported my graduate studies. Georg Wüst was the chief scientist on the Meteor in the 1920s, where they did a complete survey of the tropical Atlantic and the South Atlantic. There's a picture of me in the lower right with Georg Wüst in 1969 when he retired in Erlangen in Germany. Wüst published in 1965 a book on the Caribbean Sea and stratification and circulation of the Antillean Caribbean basins. And my name appeared on it as with the assistance of Arnold Gordon. So I don't know if I can count that as my first publication or not, but it was an honor to be part of that effort. My PhD thesis, which was finished in 1965, dealt with the Caribbean. And the Caribbean Sea, one of the figures from my thesis is that the flow through the Caribbean Sea into the Gulf of Mexico is about 28 sverdrups. A sverdrup is 1 million cubic meters per second. About half of that comes from the North Atlantic and half of it comes from the South Atlantic. And the part that comes from the South Atlantic, 10 to 15 sverdrups, was part of the global overturning circulation driven from the production of North Atlantic deep water. We didn't yet have a name for it back then, but now it's known as AMOC, the Atlantic Meridional Overturning Circulation. It was well known from the time of the Meteor that this was going on, that the upper layer of the Atlantics were going across the equator to the north, and at 3,000 meters, you had the return flow of North Atlantic deep water. So from the tropics now, I then went to the polar regions, where I led the Eltanin Circumpolar Survey from 1962 to 1978. The last few years were when the Eltanin was taken over by the Argentinians, and it was called Islas Acadas. That was from 75 to 1978. There's a picture of the Eltanin right over there, and there is one of my oil paintings of the Eltanin over there. We surveyed all around Antarctica. From in the Pacific, heading into the Indian Ocean, and then with the Islas Acadas, we did the South Atlantic, and there was also some work from the Lamont ship called the Conrad in the Southwest Indian Ocean. And together, that gave us this circumpolar view of the Southern Ocean. The technology we used was was still the technology that was used during the Meteor times. There's me with a Nansen bottle where we just measured the temperature and salinity in a water sample for oxygen chemistry, going down to only 23 levels from the top of the ocean to the bottom. So not very high vertical resolution. Standing here on the Hero platform, attaching a Nansen bottle to the cable and slowly lowering it down. Nowadays, from ships at sea, there's more electronic sensors, the CTD, which measures temperature and salinity and oxygen, and other sensors. Now, from the top of the ocean to the bottom at resolutions of 1 or 2 meters, we're getting a lot more information. It was difficult working in the Antarctic. These cruises were 60-day long, took a long time to get there. Also we had to fight the ice and very high waves, 100-foot swell at times. But it was fantastic to work in that remote part of the world and make discoveries. So observations I've made opened up many new doors to the behavior of the ocean. And I can't review them all at this time, but first we're going to talk about the Southern Ocean. So in 1973, a new satellite went up. It measured microwave emissions from the Earth's surface, and the sea ice cover had strong emissions in microwave. And what was discovered in the austral winter of 74, 75, and 76 was right there in the middle of the Weddell Sea, near the Greenwich Meridian, was an area that was not covered by ice. How could that be? It's in the middle of the winter. What could form this, what we now call a polynya? This would have been called the Great Weddell Polynya. And I'm always amazed that when this satellite was turned on, in 1973, might have been late 1972, we saw this Weddell Polynya. One might therefore think, since the ships did not go into the winter ice at that time, that, not on purpose anyway, that probably was there all the time. And of course, it was not. It was a unique occurrence that has not happened since then. So it was, if that satellite was not turned on in the mid-70s, we probably would know nothing about the Weddell Polynya. However, when I was working from the Islas Acadas, this was January, February 1977, just about in this area right here where the Polynya was earlier in the winter, which I didn't know, we made measurements of the temperature and salinity versus depth with a CTD, and we found that the usual temperature maximum of only about 0.5 degrees at around 200 meters in the Weddell Sea was not there any longer. This was the pre-thermal profile and measurements made in 1973, pre-Polynya, where the measurements that I made were over here. They were a lot colder, about a half degree cold. In fact, it didn't even go above 0 degrees any place in the water column. The salinity was also lower. Quite homogeneous temperature and salinity. And at the time, I deduced that there must have been convection down to 2,800 meters, open ocean convection in the middle of the Weddell Sea, down to about 2,800 meters or about 3,000 meters. I did not know about the microwave imagery at that time, that there was a Weddell Polynya. But when I got back, I did find out about that. And I realize now that that missing heat was caused by deep reaching convection to about 3,000 meters that then inhibited the sea ice from covering that area, something we call now a sensible heat polynya. I'm not going to read all the words on every one of these slides. I assume this will be made public, the PowerPoint, and if everybody can feel free to look at it and study it, and there's even some notes in the notes section. Contact me if you have any questions. But it was quite clear that there was a probably 2 to 3 sphere drops of overturning going on every winter for those 3 years, completely ventilated and modified the deep ocean in the central part of the rim. So then I wanted to find out what happened, what was so special about the mid-1970s that allowed this deep reaching convection to happen. And working with Martin Bisbeck and Joey Camizo, we lay the blame on the Southern Annular Mode, SAM, one of the climate indices. And during a positive SAM, the warmer air moves over the sea ice region, and the colder, dry air from Antarctica doesn't extend as far out. over the open ocean, over the sea ice zone. And the salinity decreases in the sea ice zone because of more storms from the westerlies, more rain, more snow, and that. And as the salinity decreases in the upper layer, it becomes more insulated from the warmer deep water, that subsurface water at around 200 meters that I mentioned. During a negative SAMS, the colder air from Antarctica, cold dry air, extends further out over the sea ice zone. The circumpolar belt is currents are further north. There's the storms don't make it as into the sea ice zone as readily, as commonly as during a positive SAMS. And the salinity increases over the surface layer, which decreases the strength of the picnic line that separates that cold surface layer from the warmer subsurface water. So I looked then back to see what SAMS was doing back to 1880. And there's the Weddell Polynya, this yellow box there, mid-70s. And there was a prolonged period of a negative SAMS at that period, this type. So I deduced then that this must be that the negative SAMS decreased the stability of the surface layer, this density difference between its cold surface and the warmer deep water, and eventually convection set in. Cold water down, warm water up, the polynya formed. There were other periods where there were negative SAMS, though nothing as long, nothing as, there it is, nothing as prolonged as that negative SAMS from this, from the late 60s through the 70s. There was one in 1954. And there's possibility of a polynya. There's some early Argentine data during the IGY of 1958. And that might indicate that the stratification was not there. There were other periods here. Now, an interesting story that I tell in this publication over here, my 2012, was that this is the Deutschland cruise was in 1912. And that was a period of prolonged negative SAMS. Did a polynya happen then? The Deutschland data sort of suggested that there was deep reaching convection. And Wust, my advisor, in 1928, interpret that Deutschland data as if there was a representative deep reaching convection in that area. But then we did no longer had much of, then we had long periods of positive SAMS in the mid-30s when the Discovery British program collected data around Antarctica, and they did not find deep reaching convection. So this idea of deep reaching convection that was suggested from the 1912 Deutschland data sort of lost its attraction and mainly was lost to the history of oceanography and only now to be rediscovered in this recent period. So that's just some schematics that review all of this. So here's a positive SAMS, prolonged meaning that it's relative to the residence time surface layer. So this salinity effect can, integrated salinity effect can have play a large role. So during a positive SAMS, there's the cold, low salinity surface layer. There's the picnic line separating it from the warm water, and it's stable. You don't have, do have some heat mixing up, but not deep reaching convection. With a negative SAMS, when it is drier in this area and the surface layer gets saltier, the picnic line possibly is destroyed, goes to, disappears, and you have deep reaching convection. And that is how I explained the Weddell Polynya. Now, in the glacial phases of the past, there was a few things that happened that made me believe that the Weddell Polynya was the common mode of deep reaching convection that we saw in the 1970s, or the Deutschland saw in 1912. First of all, the glacial ice of Antarctica extended to the shelf break. Sea level is 130 meters lower. Therefore, you did not have the formation of dense shelf water on the continental margin that then cascaded into the deep ocean to form Antarctic bottom water. And you had a very strong negative SAMs as the westerlies shifted towards the equator and the cold, dry air from Antarctica extended further north. So I believe is that during the glacial period, the deep-reaching convection in the Weddell Gyre and maybe the Ross Gyre in the Pacific was a common mode of ventilating the deep ocean. And what makes it even more attractive is that when this warm water comes up to see the atmosphere, it's only there for 1 or 2 days before it gets cold enough to sink. That's not enough time for CO2 from the atmosphere and ocean to be exchanged. So you start, the ventilation does not remove the carbon dioxide dissolved in the sea, in the deep seawater. So you have a greater inventory of CO2 in the deep ocean, less in the atmosphere, which may have something to do with the glacial periods. What about the future? The SAMS is becoming more positive as we have more and more global climate change, anthropogenic climate change and warming. And this is what SAMS has been doing since the 1955. It's a 12-month running mean over there, the black line. So SAMS is becoming more positive. So the Weddell polynya is going to be a thing of the past. Not going to occur very common, if at all, any longer. So that fortuitous measurement by the microwave satellite of the mid-70s, if that didn't happen, we would have a very different view of what was going on convection-wise in the Weddell. It was okay. Well, then in the 1980s, I tried to reach Maud Rise, where the Weddell polynya sort of initiated. The first was on Mikhail Somov in 1981 on a Soviet ship. There's me and Eddie Sarkanyan, the chief scientist of the ship. We couldn't get all the way down. The ice was too thick and the Somov wasn't really an icebreaker. So we couldn't get to Maud Rise. In 1986, we did on the Polish stern, the German vessel, and we were able to get into the Maud Rise area. And we were able to see that in the Maud Rise area, which is the Maud Rise is like a seamount, like a pedestal of shallow water, and in that area, you have a unique ocean stratification, and that is prone to forming a small polynya in that area that we think might have triggered the large Weddell polynya when the SAMS index was right. In other words, negative. But it was in the other place that in the Weddell that we were not at was the western part of the Weddell Sea, where there is perennial ice along the eastern margins of Antarctic Peninsula, thick ice, 3 meters thick. Can't get in there and ship unless you get stuck in the ice. You're not going to go in there and do research. So it occurred to me that I started a conversation with the Arctic Antarctic Institute in Leningrad in the late 80s, because the Russians or the Soviet Union had a lot of experience in working in ice stations in the Arctic. So I thought, let's have an ice station in the western part of the Weddell. The ice station is, you have a team of people there with instruments and housing, and you're living on the ice flow as the ice flow moves slowly across into the western Weddell, and you can collect the data. So there's the official signing, Kanilov and myself in 1989 with the Soviet Union. The work was carried out in early 1992 with Russia. There's the team over there in front of one of the bunks, and I'm in here someplace. And there's some various pictures of working through holes drilled in the ice and lowering equipment. There's the mess hall on it, and various plaques of celebrating the ice station Weddell. Lots of penguins to keep us company. Next slide. And what we did was that we put the people and set up the ice camp here at the southern part of the western Weddell, the southwestern Weddell, found appropriate ice flow, a thick ice flow, set up the camp. The ice flow slowly migrated northward with the ice flow, drifted northward with the ice flow. We had a helicopter that could do transects of temperature and salinity from the ice flow up to the continental margin of Antarctica, the continental shelf of Antarctica. And we started in February at the south. The ice station ended in June of 1992. The ship came down, got everybody off. Interesting that this is the area where the Endurance sank. The Endurance was crushed and sunk in this area. Shackleton here, there's the Endurance. And it was a remarkable story, of course, as they then lived on the ice flows and eventually made it up to the island here, South Georgia, was it? And were all rescued. Nobody was killed. Unbelievable. Tremendous leadership by Shackleton. Valery Lukin was the head of the ice station. He certainly was most important in having it as a success. Jay Ardai was from the US side, was with his tremendous talents of just making things work and in difficult environments was a large part of the success. Interesting that where the Endurance sank, the ice flow also experienced some problems, that the ice flow that the ship that the camp was on started cracking and breaking apart. Things had to be moved and things like this. So we believe that has something to do with the Endurance ridge here that caused the construction or a convergence of the sea ice as the circulation then slowed as it approached the ridge. But the wind kept pushing it north. So now, so what we did, this is one of the helicopter sections, helicopter section 3, this thing in red here shown. And so this is an example of what we found as we went from the continental shelf into the deep ocean. So here is the upper 1,000 meters for temperature and for salinity, and there's from the surface down to the sea floor for temperature and salinity. And we see here that there was there's that warm deep water, that 0.5 degree, relatively warm Weddell deep water over here. And there's this thermal front that separates this warm water from the cold waters on the continental shelf. This is a temperature gradient, the picnic line that separates that. But here in salinity, we show this V-shaped trough of the isohalines, where there was a convergence of water here, and it was sinking in this region. And that's right on the left side, on the landward side of that, that's where the shelf water was escaping. And to cascade its gravity currents into the deep ocean and then move northward at about 10 to 15 centimeters a second northward in the Western Weddell to finally reach out and spread into the world ocean. February 13th, 2017 in St. Petersburg, we celebrated the 25th anniversary of the ice station Weddell. There's some of the people who are on it, looking a little bit older, I suppose. There, I'm giving a little speech, being translated in Russian. That's the captain on the Fedorov, which was the Russian ship that set up the camp. And you might be surprised to know that they drink a lot of vodka there. What we did after the ice station was then set up some moorings in this area to try to get a long time series of the escape of the Antarctic bottom waters formed in this area that we studied with the ice station Weddell. And that started in 1999. And that's when we discovered something we didn't expect. There's a strong seasonal cycle to the export of Antarctic bottom water in this area. that the coldest water, we passed by these moorings right here in like June. But using typical velocities in here and knowing where the water comes from its temperature and salinity, we knew the shelf water had to escape into the deep ocean in like December, 5-6 months earlier, something like that. That the bottom temperatures, this is we're monitoring the lower 500 meters. So this is color coded for the distance from the bottom. The black is at the bottom, and this upper, the darker black up here is from thicker line is 500 meters above. And you'll notice that the biggest seasonality to the signature is at the bottom. This means this is a gravity current driven by the high density of the bottom water, velocity driven by that. We saw that there was variations, interannual variations beside the seasonal variations. Times there were cold pulses and you had a lot of cold water, other times it didn't happen at all. We looked into that and we found that it had to do with the wind. That when there was strong wind to the north, flowing to the north in the western Weddell, that you generally had warmer bottom water escaping from the western Weddell. When the winds relaxed, like in this period here in around the year 2000, then that there was colder water passing by. So somehow stronger winds seem to inhibit the escape of the shelf water. Strong meridional northward winds seem to inhibit the escape of the shelf water. And when the winds weakened, the shelf water can cascade into the deep ocean as a gravity current. And to understand this, this was a simple picture of, I think I'm going a little too long here. A simple picture of the shelf slope front, seaward in the summer, shoreward in the winter time, proportional to the stronger winds in winter in the Ekman transport and weaker winds in the summer. And this was like a gatekeeper. You form the dense water in here. When the shelf water was able to migrate seaward, the dense water can go over the side. You can look at this later. Another, the second area of observations that were made was here in the south of Africa. This was a cruise I did in 1983. And that was an interesting discovery. Just this background, the Anomalous current, the western boundary current of the South Indian Ocean, rounds the bend here in south of Africa, but most of it retroflects and goes back into the Indian Ocean, the Anomalous retroflection. Anomalous about 70, 100 sphere drops. I was working in this area and I was really surprised to see Indian Ocean water there, big pools of Indian Ocean water or eddies of Indian Ocean water. It was quite clear that the Indian Ocean water was leaking into the southeast Atlantic, Anomalous leakage, which made the Benguela current saltier than would otherwise be if you didn't have the leakage of the salty Indian Ocean water in there. And this is an important part of why the Atlantic is so salty and why the Atlantic is the site of North Atlantic deep water, the AMOC, the Atlantic Meridional Movement Turkey circulation, was that this area here is saltier than it would otherwise be if there were no leakage. And that water slowly, some turns back into the Indian Ocean, but parts of it continue up along the north coast of Brazil, into the Caribbean, into the North Atlantic, and keep the area salty and prone to deep convection in the North Atlantic deep water. This led to a global kind of circulation, interocean circulation pattern. I call this the warm route, the surface layer coming from the Pacific through Indonesia, Indian Ocean, around the bend, around the southern rim of Africa, into the North Atlantic. And then that water sinking in the North Atlantic and the North Atlantic deep water, a few thousand meters to hollow arrows, spreading out through the ocean, and it was closed. And there's all sorts of schematics now of the overturning and global interaction, global interocean exchange pathways and global circulation. Phil Richardson has a very nice history of that in Progress in Oceanography. Well, it was quite obvious. If the Indian Ocean is leaking into the Atlantic here, where is it coming from? I did some work in 1985 and 86 to indicate that it was coming from the Indonesian Throughflow. This is the temperature and salinity in the thermocline of the Indian Ocean. And there was Pacific cooler, lower salinity water at about 10 degrees south, spreading westward, Indonesian Throughflow. And that, I believe, was what was feeding the Agulhas leakage into the Atlantic as part of the global circulation. I knew had to swim upstream to the Maritime Continent, to the Indonesian seas, and measure that. That has no one worked in that area for quite a long while. So it took a long period of time to find out, working in the area, how to get the approvals to work in the area. And finally, in 1991 into 1998, we had our first program with the Indonesians called Arlindo. The first part of the Arlindo program was to see what are the pathways for the Pacific water to weave its way through this complex geography of the Indonesian seas. And we found the primary one was here in Makassar Strait, this little narrow channel about 40 kilometers wide there. That's with pure North Pacific water flowing through that area. There was some waters flowing through the eastern channels, but nothing as rigorous as or as vigorous as the what was flowing through Makassar. And we now know that Makassar throughflow is about 80% of the total throughflow. The total throughflow is about 15 sphere drops. But another discovery we made when we put moorings out here in this Lambani channel, right over here, was that this was also an unexpected discovery. Up until then, the Indonesian throughflow was assumed to be surface intensified. In other words, really warm water coming through the surface. Wasn't that way at all. We found that the strongest velocities were at about 100 to 200 meters. There was a subsurface maximum in the thermocline. The transport weighted temperature was much colder than originally thought, about only 15 degrees rather than like 25 degrees. So that became important. However, the throughflow, the mountain water getting through there was only 8 sphere drops, but this was a very strong El Nino. And as a strong El Nino, the pressure gradient between the Pacific and the Indian is weaker. There should be weaker transport. And therefore we knew we had to go back there. And we had then a big international program where we measured the throughflow in all the key channels in this region over a 3-year period from 2004 through 2000 to the end of 2006. Okay, same thing. This is the velocity, red strong to the south, and greens close to 0. And the velocity maximum was in the thermocline at around 140 meters. The transport was about 12 sphere drops, 30% higher. The transport weighted temperature was about 0.5 degrees warmer than it was during the Arlindo period. So it was the El Nino period during 1990s that decreased the flow of Pacific to Indian water, decreased the amount of the Indonesian throughflow. In the 2004 to 6, the El Nino, La Nina oscillation, and so it was pretty much neutral at that point. So this was a better view of climatology. Why is there a subsurface maximum in velocity? What's holding back the surface waters from the Pacific from flowing into the Indian Ocean? Well, this is what we now call the freshwater plug. In this area of the Maritime Continent in Southeast Asia, the surface salinity is very low because of excess precipitation, large rivers flowing into the area. Low salinity makes that water very buoyant. It goes down to about 70 meters surface layer. And that inhibits the warmer waters from the Pacific from from flowing into the Indonesian area. In fact, the pressure gradients now are actually reversed in the upper 50 or 70 meters. And that gives this annual cycle with the highest velocities in the austral summer, lowest velocities in the winter. But there's also interannual variability. And that's because the freshwater in the South China Sea is exported into the Indonesian seas when there is through flow through the Luzon Straits, when you have Pacific water flowing through Luzon Strait, which happened in the El Nino, and it also happens in the wintertime. So the freshwater here, the freshwater plug is put in the face of the Indonesian through flow during El Nino, during the winter. In La Nina, there is near zero flow through Luzon Straits. So this water is not flushed out into the Indonesian through flow region. The fresh water can become accumulated there from the river and excess precipitation, basically recharging the freshwater content. So during El Nino, water coming through Luzon, and the water goes through into Sulu Sea, and it inhibits the through flow from coming in to Makassar Straits in the upper 70 meters or something. And during La Nina, there is no through flow coming from the South China Sea, no discharge of the low salinity South China Sea water into the Indonesian through flow region. So you have less of a freshwater plug. We put together the 3-year view of instant, and I won't say too much about this now, but Makassar is around 11, 12 sphere drops, and most of that's going through either side of Timor Island over here. Another thing we discovered during the Arlindo program was that the stratification coming in from the Pacific Ocean the salinity stratification is almost completely removed as the water weaves its way into the Indian Ocean. And it's removed by very strong vertical mixing, primarily driven by dissipation of tidal energy. So there's a schematic. I like to do schematics. And you have the waters coming in from the Pacific with a maximum at around 100, 200 meters. The water is mixed here rapidly, vertically, enhanced vertical mixing because of the tidal dissipation of tidal energy. And that makes that water more buoyant, and it starts to then get pushed up by the new water coming in and upwells into the surface layer. The outflow into the Indian is at a slightly shallower level than where the water came in. The surface water here is colder because of the enhanced vertical mixing. And this becomes important in trying to understand the convection. You can look at this later on, this figure in here, of the atmospheric convection. This cold water is slightly colder than it would otherwise be if there weren't the tidal enhanced mixing. That inhibits the convection over the central part of the Maritime Continent. The bottom line of that is that if you really want to get ocean atmosphere right and the climate right, your ocean component has to include tides. If you didn't have tides, you would not see the reduced convection of the atmosphere in this area. So now on to the recent observations that we have made here of, and I see I'm running out of time, but we did some time series of the through flow through Indonesia and time series of the outflow of the Weddell Sea Bottom Water. And here for the extended time series of started in Arlindo in 1997, actually was the one we put the moorings out, and going to 2017, August 2017. You can see, you can see the, that you have the seasonality, but you have interannual variability, La Nina periods here when the pressure gradient is stronger from the Pacific to the Indian, stronger through flow than it was during El Nino. And in the surface layer, you sometimes get these reversals of flow. And it was in this period in here from 2015 to 2017, it looks quite different, much stronger flow down at depth in here. Actually, northerly flow in the winter times winter times down to almost 100 meters in the surface layer, upper 100 meters. And also in the summer of 2016, all of a sudden the flow went to zero, where ordinarily we had strong flows in the summer. These are the references that talk about that. My message here, when you think you understand a time series, it might be a good idea to stop making further observations unless you want to make further discoveries. Keep observing the ocean. Lots of surprises out there. I'm going to have to move along a bit faster, but the surface layer reversals in here had to do with strong Madden-Julian oscillations passing over the Indonesian seas of the Maritime Continent. And what the Madden-Julian oscillations do is take fresh water out of the South China Sea through the Java Sea and put it into the to Makassar Strait, inhibiting the upper flow. And you can read about that in the papers by Napito et al. In 2019. Whoops, sorry. And then this the summer relaxation of the flow, that was also strange in that, and it looks like, and that's in the paper here by Kandaga Pujana and et al. 2019, a special issue of JGR. And it was a very strong negative IOD in that summer, not clear why. And what that did was it made the sea level in the Eastern tropical Indian higher than would otherwise be in the summer, and that decreased the pressure gradient from Pacific to the Indian, decreased the through flow. And these are all areas of study now, the effect of Madden-Julian oscillations, the interaction of ENSO and IOD, and even the South Asian monsoon. Another thing that happened, it's surprising, in 2015 to 17, was that the ratio of the upper and lower transports, which ordinarily were 3 to 1, the upper 300 meters, like 9 sphere drops, from 300 meters to the sill depth at 760 meters was about 3.4 sphere drops, 3 to 1 ratio, all of a sudden became 1 to 1. Something enhanced the upper level, the lower level circulation. That's coming, as you can see here, from the South Pacific. And we now know, and in fact, Vertke in his paper in 1989 suggested that the South Pacific subtropical gyre lags behind El Nino episodes by about, by about a year or two, something like that. And so we think that this had to do with the 2015 El Nino that decreased the upper layer flow, and then a year or two later increased the flow below 300 meters, which is South Pacific waters. But then the transport here in 2019 and 20, but in late 2017, reached 20, there's the total transport, it reached 20 sphere drops, about the strongest through flow we've ever seen before. It's likely that the upper layer, when the El Nino was over, got more water coming in from a La Nina, but the deeper layer still was responding to a previous El Nino. So the combined effect was a very strong flow. Heat flux. What about the Indian Ocean? The heat going into the Indian Ocean. And this is the work I'm doing, a graduate student, Laura Grunberg. And what we found was that there was more heat going into the Indian Ocean through Makassar Straits during La Nina and during the summertime, the July to September, than during El Nino in the summertime. There's less heat going through in the wintertime because of this more significant freshwater plug. You can read about that in there. We have seen this paper by Lee et al. The heat content in the world ocean was going up. Heat content in the Pacific in the first decade of the 21st century all of a sudden went down. Heat content in India went up. We attribute this now to was more of a La Nina condition in the first decade of the 21st century, which removed heat from the tropical Pacific and put it into the Indian Ocean. Eventually, where does that heat go? Is it going to go around the Agulhas into the Atlantic? Is it going to have an effect on AMOC? One thing we surprised us was that we were looking at our Lindo data with Laura, the Argo data in the outflow of the Indonesian Throughflow and in the South Equatorial Current. And the box seemed to have disappeared here. Also in the Lewin Current, which is a southward flowing surface flow along the west coast of Australia. And we found that when we compared the amount of heat going in to the South Equatorial Current with the amount of heat going through Indonesia through flow, that they compared quite well, except in 2011, the heat coming in the ITF box was a lot higher than being taken away by the SEC box. Where was it going? Which we show in here, when you combine it with the Lewin box, which is right here, that most of the heat was going into the Lewin current in 2011 and not into the South Equatorial Current. Most interesting. And we think that this has to do with weaker northward winds along the west coast of Australia in 2011, less resistance to the through-flow induced southward pressure gradient along the western coast of Australia. And this had to do with a unique, what's called the Niño in the eastern South Indian Ocean. I can't go into those details there. But when we looked at the amount of Indonesian throughflow water going into the South Equatorial Current, it was lower there in 2011. So it happened from that period of 2011, the heat went down here in the Lewin Current rather than through the South Equatorial Current. That makes a big difference. This is some work I did with a graduate student way back in the 2004. And this was with a rather coarse model. And we put some Lagrangian particles in a rather coarse model, and we saw it take about that the Indonesian throughflow tracked across the Indian Ocean, the South Equatorial Current, and some went north, but eventually it all had to go south. About 50 years later, the water from the throughflow goes into the Agulhas leakage. A higher resolution model, there's too coarse to see the Lewin current. The higher resolution model that was done here in Doragadu et al. Paper 2017, that sort of suggested that some of the throughflow water may be going into the Lewin current. He had this arrow in here that some of it could be doing that. So the ratio of the heat going into Lewin and to the South Equatorial Current really changes interannually. What's the impact on the Indian Ocean, the distribution of the heat in the Indian Ocean, and what's the impact on that heat eventually getting into the Atlantic? Research in progress. Getting close to the end. All right, we see something strange in the Weddell Sea Bottom Water in that 2015 and 16. Amazing. Here's the salinity of the bottom water, and there's the temperature. There's the good old seasonality that I mentioned earlier. But here in 2017, the salinity of the bottom water reached an all-time low. And when you look at the TS diagrams, the only way we can explain this low salinity is by having water coming that the cold end member was not the continental shelf waters along in the western Weddell, but actually open ocean winter surface layer water. This is discussed in this paper in 2020 in GRL. So something changed in 2015 that shifted the cold end member from continental shelf water escaping as gravity currents to open ocean winter surface waters, which were found in the middle of that trough that I talked about earlier. So what happens is the cold end member for our 2016 were coming from the waters within the trough, this water right in here, rather than from continental shelf water. Why was this the case? Once this gets deeper, when that V-shaped curve gets deeper and deeper, the thermobaric effect can make that colder water more compressible, and it goes down to the bottom. Another thing happened in 2014 and 15 was overmoored rise, which I mentioned before. All of a sudden, much more common to see opening of the sea ice, Weddell, the moored rise Polinia, occurring over periods of many weeks there, right over moored rise in that region, more so than it did in the past. What was happening? Why did the bottom water change? Why did we get more of moored rise? Well, so we think what was happening in here was that there is a, during this period of time in 2014 to 2017, the wind curl, the wind over the Weddell Sea increased so that you were getting more cyclonic vorticity put into the ocean. The Weddell Gyre spun up. As the Weddell Gyre spun up, the picnic line went up over moored rise, bringing warmer waters to the surface, more conducive to moored rise Polinia. In the western part of the Weddell, this V-shaped trough would have descended further as the picnic line dipped downward to accommodate geostrophically the stronger northward flow of the spun up Weddell Gyre. The only thing that we can see that was strange about this very strong Weddell Gyre spin up was both SAMS and El Nino were strong and in phase. That has not happened before. Usually they're out. This is SAMS here in 1998, and there's El Nino. They didn't occur at the same time, a little bit later. Had moderate spinning up of the Weddell Gyre, but we didn't see any big change in moored rise Polinia or bottom water formation as we did here, both strong and in synchrony with one another. Another thing strange, paper by Claire Parkinson, the sea ice in the Weddell, or this is the Southern Ocean sea ice, but also in the Weddell, where ordinarily the sea ice in Antarctica have been getting about the same, or actually getting a little bit more extensive in recent decades. All of a sudden in 2015, it reached lows. So the moored rise, less sea ice, change in bottom water. So look, my goal here, and this is my last slide, is that my goal here is to highlight recent changes in the tropical and southern polar regions. They must be linked, but why? What's happening? Is this the precursor to some rapid changes precursor to more rapid changes of wording wasn't right, precursor to more rapid changes. And I think yes, and I think these observations will show us how to deal with this and how to explain it. The ocean and climate system is a complex array of springs, you might say, with different Hooke constants, and they all interact internally with one another. Of course, there's some external factors too, such as the Earth's orbit, but internally you have El Nino and SAMS and a host of other climate oscillations that interact with one another at various timescales. And this is a nice Jiaju Yuan of complicated figure that shows the relationship of El Nino and SAMS in that area. So somehow these things are connected. And something happened and something changed in 2014 and 15. What's going to happen in the next 5 years or so? Is that going to get worse, or it's going to go back to where it was before? This I don't know. So this is my last slide. I'd like people to study these figures that I show here. Think about it a bit. Get back to me, and maybe as a team we can work together to try to better understand these connections between the tropical and the polar areas. So I'm sorry I went on a bit long, but questions? Anybody have?
Thank you, Arnold. That was a fascinating discussion of the importance of regional oceanography to the global ocean circulation. We now have time for questions and answers, and I encourage the audience to please enter your questions in the question and answer box. And what we'll do here is I'll read the questions and Arnold is hopefully going to answer them. Okay. So the first question we have is from Carson Witt, and he says, you showed observations of a 200-meter temperature maximum in the Weddell Sea in 1973 as the pre-Pollinia condition, but the SAM index had already been negative for a decade by then. Does this suggest that perhaps a prolonged negative SAM is required to trigger the deep convection, and maybe explain why deep convection was not observed as clearly in the shorter periods of negative SAM?
Yes, yes, that's correct. You need a prolonged SAMs, negative SAMs, to build up the salinity of the surface layer and decrease the strength of the picnic line to lead to convection. And but prolonged, what does that mean? The residence time of the water in the surface layer is about 3 years. So the prolonged means it has to be more than 3 years for it to have an impact. And that's exactly why we had the Pollinia, the mid-1970s. It was a prolonged negative SAMs, started in the early 70s, or forgot when. You can look at that figure, about 1970 or so. And by 1973, 74, it changed the surface salinity enough to lead to the convection. If a SAMs, negative SAMs, only last, is not prolonged, only lasts for a few years, you don't build up that salt to develop the convection. Next slide. Next question.
Yeah, the next question is from William Kessler. He says, why is there an ITF? We think of it as part of the thermohaline circulation or conveyor belt, but Stuart Godfrey showed that its transport is accounted for by pure wind driving, no thermocline influence, and how can these be reconciled?
Well, Billy, you always ask great questions. And certainly the pressure gradient between the Western Pacific and the Eastern Indian Ocean, Western Pacific, is higher, sea level, higher pressure. It is a product of the large-scale wind field. And that's what drives the convection. The island rule that Godfrey come up with is what's doing that. In El Nino, the sea level in the Western Pacific is not quite as high as it is during La Nina, as the warm pool shifts eastward and the throughflow is reduced. So yeah, it's the wind that it's doing it, all right, that's gradients. But there is a gradient, the pressure gradient, particularly in Indian, does have a function of depth to it. And the freshwater plug is that in the upper 1,500 meters or something like that, the pressure gradient is not as effective because of the very buoyant surface layer. So there's a lot of stratification issues and shear issues involved with the interocean pressure gradient. But it's amazing that Stuart Godfrey's island rule, what did he come up with for the throughflow? 15 spheredrops. And what did we measure over these periods of years? 15 spheredrops. Pretty good. Stu.
Very good. Okay, so the next question is from Mike McFadden. He starts out by saying, great presentation, thanks for it. All right, and he asks, you emphasize advective salinity fluxes in discussion of the ITF and the anomalous. However, over Indonesia, there is large precipitation anomalies during El Nino dry and La Nina wet. This seems like it opposes the salinity tendencies from advective salinity fluxes from the South China Sea as you described. Can you comment on the relative magnitudes of these competing processes in affecting the freshwater plugs? Also, what is the relative importance of an evaporation precipitation in the Atlantic basin versus anomalous leakage in determining the salinity of the upper limb of the AMOC? Good questions. Yeah.
Oh. And there's a lot of questions there. Go ahead, Mike. Do I have to answer them now? Hey, let me first start out with the Atlantic. The latter part of that is that the Atlantic is saltier. Surface layer is saltier than the other oceans, and then its northern polar end in the North Atlantic. You cool that salty water, and that water becomes dense enough, the North Atlantic deep water, to sink and flow southward at around 2,000–3,000 meters. Okay, why is it salty? One of the sort of conventional wisdom stories is that there's evaporation from the subtropical North Atlantic, and that water vapor passes over the Isthmus of Panama, the various gap winds there where you have sea level kind of connection between Pacific and Indian, and you draw out that water vapor, and the salt stayed behind. However, the South Atlantic is also saltier than the South Pacific. And that's where the Agulhas comes in. The Agulhas is putting subtropical waters from the South Indian Ocean into the South Atlantic. The leakage. If it didn't do that, the Benguela current will draw all its water from the subpolar current in the South Atlantic, which is much lower in salinity. So I believe that the saltiness of the South Atlantic is because of the Agulhas leakage. Which is more important to the question? I think they're about 50-50. I think that the Agulhas, the salt put in by the Agulhas leakage, or really the blockage of the low subantarctic, low salinity water, versus the gap wind, so from the North Atlantic, I think it's about a 50-50. So that so that's it. The other one you have question is that, yes, the Pacific Ocean is actually putting in cooler, lower salinity waters into the thermocline of the Indian Ocean, and that water is being pushed southward. The only way out for the Indonesian Throughflow is south. Much of it goes into the Gulf retroflexion and goes back east in the Indian Ocean, but the 15 teardrops goes into the South Atlantic. So it is salty, but the primary reason why the South Atlantic gets salty is that this Agulhas leakage blocks the lower salinity subantarctic water from curling into the South Atlantic gyre. So there's a lot there. We can talk about this later because I'm pretty sure we'll run out of time here. But it's most interesting of exactly how the Agulhas leakage leads to that salty South Atlantic water. It's putting salt in, but it's not as salty as the South Atlantic water. But it's blocking the low salinity subantarctic water from going into the South Atlantic. That would have would reduce AMOC. Not a very thorough answer, but go ahead.
Good answer, though. Thank you. Next question is from Clara Reimers, and she asks, can you give any examples of deep convection outside of polar regions?
Not counting the North Atlantic too. I mean, that's a polar region. The Labrador and Greenland Sea, deep convection, Ross Sea, Weddell Sea. By the way, there's been during this period of time when we saw that change of bottom water from the Weddell Sea, there was just a recent paper published in Nature Geoscience. The name of the person. About how there's been an increase in Ross Sea bottom water, and they also blame the synchronous SAMs and El Niño too. So it's there's something very global going on in 2015 to 16 and 17. You have deep reaching convection in the Mediterranean, in the off the coast of southern France, Gulf of Lyon. You have deep reaching convection in the Adriatic Sea, in the Mediterranean, and you have deep reaching convection in the Red Sea. So in those very salty, warm seas, very salty, there's deep reaching convection. Perhaps perhaps many millions of years ago, when you didn't have the cold polar regions as you do now, perhaps it was the deep convection from these warmer subtropical areas that were the main ventilators of the deep ocean. And the only place they occur now is the Mediterranean and the Red Sea, which happen to be very salty seas. Go ahead.
Thank you. All right, the next question is from, and I apologize for mispronouncing the name, is Shilong Dao, I think. Could you please discuss more possible observational evidence for the possible Polynias event happened back into the 1990s? All right, because we run a high resolution CESM model forced by real history CO2 concentration. Our model is obviously a little excessive to produce Polynias. There are two strongest Polynia events happened in about 1990s and the 1970s. I'm not sure if our model captured some real signals or just some random phenomena, so please discuss more about possible Polynia evidence in the 1900s. Thank you.
Come on, I want to get my other computer going up here now because all right, okay, it's one of the last slides. So what happened is during the 1990s, there was the large Weddell Polynia was only during the mid-70s, as I mentioned. However, during the 1990s, particularly in 1991, 92, and 94, the Maud Rise Polynia was quite frequent. So that there was some deep reaching convection in the area of Maud Rise in the early to mid 1990s. It did not spark a large scale Weddell Polynia though. And I think the reason it didn't do that was because you didn't have a prolonged negative SAMS. So the salinity of the open Weddell Sea was not high enough to start a deep reaching convection. Over Maud Rise, much of that upwelling of the water is just due to the circulation interaction with Maud Rise, with this seamount in that area. When you spin up the circulation that you did in the early 90s, you increase upwelling around Maud Rise, giving you Maud Rise Polynia. But once you started that, it did not spread throughout the Weddell because the Weddell surface layers was not salty enough because there was not a prolonged negative SAMS. So I think we're looking at two different kind of Polynias here. One is the topographic driven Polynia, like Maud Rise, and one of them is the larger scale thermohaline driven Polynia, like the Weddell, like the Great Weddell Polynia. There's lots of papers written about the Polynias, Maud Rise Polynia and such in the recent years. So we can talk about that later on.
But there's now a correction saying he's asking about possible Polynias in 1900, not 1990. But you gave an excellent answer to the previous question.
What are you saying now? Is there, what was it now?
In the early,
I can't hear you.
He's asking about Polynias in the 1900s, not 1990s. So.
The two strongest Polynia events happened in about 1900. Well, that was, of course, as I mentioned, so the Deutschland in 1912 made some of the first measurements in that area of the central part of the Weddell Gyre, and back then they didn't take they only had about a very few data points versus depth, so you really didn't, but it did not show the high stratification. And as I said, Geo Voos then interpreted that as open ocean convection, like was going on in Greenland, the Greenland Sea, and So there certainly was deep-reaching convection in the first decade of the 20th century, and as captured by, the result of which was captured by the 1912 Deutschland data. So there was definitely a plania then. And then, though, there was no negative SAMs after that for quite a while. So when the Discovery made its work in that region in the late 20s into the 30s, they didn't see any deep-reaching convection. And the conventional wisdom was the bottom water was formed from dense shelf waters on the continental shelf that then cascaded into the deep ocean. And Wust, in that 2012 paper that I saw in the slides there, forget what it was in, Nature, I think it was a Nature commentary or something. Wust then changed his mind and did not about the deep-reaching convection, and went along with what Deacon and saw in the Discovery. But I'm pretty certain there was deep-reaching convection in the first decade of the 20th century, and it's too bad that but that it did not occur again until 1970s.
Okay, thank you. All right, any other questions from our audience? Well, we have a little bit of time, but I have one question for you. You in your presentation, you showed very well the importance of the regional, what goes on in regions to the total global ocean circulation. And a lot of that is changing now. Is there any one region that you would highlight as a place to watch over the next, 50 to 100 years that will have the most impact, perhaps, on the larger scale ocean circulation?
Yeah. I think what's going on now, I think the changes we're seeing in the Southern Ocean are very dramatic in the last 5 years. And I think we're seeing just the beginning of an extended period of changes in the Southern Ocean. The tropical climate and the polar climate, the Southern Ocean, they are linked. It's a global system after all. So all these factors that are changing the through flow that I spoke about are also changing the Antarctic area. And I think that I think that it's the Southern Ocean that's the place to watch over the coming years, because I think we're going to see extraordinarily dramatic changes there. The sea ice has generally been staying the same in the winter, even increasing a little bit. All of a sudden in 2015, all around Antarctica went down sharply, has not recovered. The bottom water changed in the Weddell. It became less salty as more surface water was coming in. Is that going to be a sign of the future, that Antarctic bottom water coming from the Weddell Sea is going to be composed of open ocean winter surface water rather than continental shelf water, which is going to get less salty because of the melting of the glaciers? In the Ross Sea, a similar thing. All of a sudden, there's been a change in the Ross Sea bottom water. So I think looking at the Southern Ocean overturning and the Southern Ocean sea ice, I think we're seeing the beginning of a very dramatic change there. And it's linked, sparked, I like to use the word, by the tropics, not independent of the tropics. But until now, the Southern Ocean has been more resistant to these changes. And I think that period is over. Okay.
No, that's thank you. Do we have any other questions from our audience? We're coming up on our time here, but if we do, we'll take one or two more questions. If you put them in the question and answer box. Okay, give it a moment here. And here we go. Okay, so if not, then what I will do is thank you, Arnold, very much for a wonderful presentation. It's great, and it certainly embodies everything that Sverdrup would have wanted to see in a Sverdrup lecture. So thank you very much. I also want to thank the AGU staff for making all this possible, the people from Intrado that did this to make all of this work in such a seamless way. And I want to thank the audience for your participation in the virtual AGU meeting this year. So thank you all, and look forward to hopefully seeing everyone in person at the fall AGU meeting next year. That will be in New Orleans. So thank you all very much. Okay, thank you.